Hello, good morning. Let's continue with this 4.2. The next part that we will do here is to graph some exponential functions. Let's try number 13H. This from number 13H. We have graph fx equals to 2 to the negative x, 2 to the negative x. So the basic function will be two to the x, which, hold on, which is, the graph looks like this. The graph looks like this, right? Okay, now then 2 to the negative x, then you replace x by negative x. Is x replaced by negative x, right? Now, which means reflect with respect to y-axis. So the graph later on will be like this. Is it okay? Yeah, that's what it will look like. Now, let's sketch the graph. Give me a second. I think I did it incorrectly. Let me put the graph here. So the y-intercept, the graph supposed to look like this. This is 2 to the x. This is what 2 to the x looks like. That's what 2 to the x looks like. Now then, when you reflect with respect to y-axis, then the y-intercept, of course, stay the same, right? 2 comma 1 becomes, I'm sorry, 1 comma negative 2, 1 comma 2 becomes negative 1 comma 2. Negative 1 comma 1 half becomes 1 comma 1 half. And so on and so forth. So 2 to the negative x will look like this. This is y equals to 2 to the negative x. Okay, now of course in your quiz or in your test, you don't need to sketch this one. I just try to give you the picture why it looks like this red one here. Okay. I think that one is basic enough, right? That one is basic enough. Now, if we go on with, for example, number 13J, it is graph fx equals to 2 to the 3 minus x. Now, what will that be? Again, the basic function is is 2 to the x, which is the type of exponential function I usually ask base 2. Now then we will replace x by x plus 3, right? Which means we move 3 units to the left. The 3 important coordinates now will be here. Okay. Now, originally it's here, right? Now you move it 3 units to the left. Now, and then we will replace x by negative x. Replacing x by negative x, that gives us 2 to the 3 minus x. But again, replacing x by negative x is reflecting with respect to y-axis. Okay, that's what it looks like. Now let's put them into practice. So originally, those 3 important coordinates were here. Actually, if I can add, just to help out with the graphing, it's one more here. Now then, 2 to the x plus 3 means you move 3 units to the left. So this guy move here 3 units to the left. 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 You see that? Okay. So the new graph 2 to the x plus 3 is now here. Now then, reflect this with respect to y-axis. So this guy becomes here, this guy becomes here, this guy becomes here, this guy becomes there. Okay, so 2 to the x plus 3 looks like this. Right? Okay, now then, when you reflect with respect to the y-axis, then we get this. Okay, let me do the shadowing. This is y equals to 2 to the x plus 3. Well, the one we need is y equals to 2 to the 3 minus x, which is basically replacing x by negative x. Now, suppose we have more transformation involved. Let's say, for example, if I have let fx be 2 to the 3 minus x minus 4. 2 to the 3 minus x minus 4, which is basically the graph we have earlier, but we drop down 4 units. Okay, but this time we'll answer more questions instead of graphing it directly. Let's answer the following question. Part A, find the domain. And then how about the range? How about the y-intercept? How about the x-intercept? And how about the asymptote? Before we actually graph it. Now, the domain of exponential function is always all real numbers. You can plug in any x you like. Okay, but the range we know is not all real numbers. Okay, but we have this, again, we repeat the process. 2 to the x, the horizontal asymptote is y equals 0. Okay, 2 to the x plus 3, you move 3 units to the left. Horizontal asymptote still y equals to 0. Replacing x by negative x, that's reflection with respect to the y-axis. That will still be horizontal y equals to 0. And then you drop down 4 units. Then the horizontal asymptotes now goes down by 4 units, right? So the horizontal asymptote is now y equals to negative 4, right? That's y. Let me answer part E first. Y equals to negative 4. And we know the graph is decreasing, right? So the range will be from negative 4 to infinity. Okay? Now, by the way, I prefer you to look at the graph, right? See how the graph dances to these effects that you need. But it is also possible to actually work it out this way. It feels weird because the 3 is a negative. The 3 is a negative. Yeah, the one we replace is only the x. Yeah, the one we replace is only the x. So it's actually the 3 there, okay, will actually move left, right. Now, you may wonder why we moved 3 to the left. Is it right? Okay, I have this question. It feels weird because the 3 is a negative. That's our friend comment. That's true. I feel the same way. Okay, about this guy here. Why is it when we replace x by negative x, x by x plus 3, the graph moved 3 units to the left? The way we think is like, to move it 3 to the left, you're supposed to subtract by 3, right? The idea is this. Think of that as if you play the movie 3 days ahead. Think of it that way. You play the movie 3 units earlier. So instead of the movie start at 0, let's say, it starts at negative 3. Yeah, the effect of the graph will be the same. The effect when x equals to 0 here, that is 2 to the 0, will be the same to when x equals to negative 3 here. That will give you 2 to the 0 also. Okay, that's why then it becomes move 3 units to the left. Okay, now going back to the range, beside looking at how the graph actually move, we can also see it this way. Now, but the following is not something I really like, but it's doable this way. Okay, now think of it this way: 2 to the x is at least is more than 0. Okay, we know that from the basic function. Now, so replacing x by x plus 3 will not change the range. Okay, that's replacing x by x plus 3 only shift the graph left, right. It's not shifting the graph up or down. Now, replacing x by negative x is reflection with respect to y-axis. So that kind of movement is also left-right movement thingy, like you reflect that with respect to y-axis. It will not affect how it moves up or down. Now, only when you subtract by 4, then you subtract this 0 also by 4. Okay, now from there, then you see this 2 to the 3x minus 4 will be more than -4. Okay, that's the explanation. More into the algebraic explanation instead of looking at that from the graph. Now you can try to connect these two ideas here. Okay, looking at the graph and seeing that from algebra point of view. Okay. Now, how about the y-intercept? Well, we will replace x by 0, right? So f0 equals to 2 cubed minus 4. That's 8 minus 4. That's 4. So the y-intercept is 0, 4. While the x-intercept, we will replace the y by 0. And then solve for x. So by 1 to oneness, 2 equals to 3 minus x. From there, we see x is equals to 1. So the x-intercept is 1, 0. Now, let's plot this graph using what we have here. The y-intercept is 0, 4. The x-intercept is 1, 0. Okay, and then the horizontal asymptote y equals to -4. That's y equals to -4. Now, don't forget, we have 3 important coordinates to talk about. Okay, 2 to the x has these 3 coordinates, important coordinates. Move 3 units to the left. Give us this. Reflect with respect to y-axis, this guy becomes that. This guy becomes that. This guy becomes that. And then move down 4 units. This guy becomes here. This guy becomes here. This guy becomes here. Shouldn't it reflect first, then move to the left? No, moving to the left is when you replace x by x plus 3. So if, let's see, if you start with 2 to the x, right? And then you reflect, this is what it looks like, right? Now, then when you move 3 units to the left, you replace x by x plus 3. You replace x by x plus 3. But what you get is 2 to the -x minus 3. Remember, moving 3 units to the left is replacing x by x plus 3. Okay, but because you have negative in front of that, then you should distribute the negative also. Okay, yeah. No, don't say sorry about that. That's a very common mistake, which I myself actually thought that way until my teacher also explained pretty much the same way when you replace. That's why we never say that, oh, you add 3. I never only say you add 3, move 3 units to the left, right? No, moving 3 units to the left is replacing the x by x plus 3. Okay. So when I replace that x by x plus 3, but I already have negative in front of that, then I have to distribute that also. Okay, that's a That's a very common concept that you and I had that. Oh, I also have that before. So don't feel bad about it, you know. Okay. Now once we have these three important coordinates, x-intercept, y-intercept, and horizontal asymptotes, then we are ready to graph them. To connect these dots here, right? We have, oops. This is approximately the graph of y equals to 2 to the 3 minus x minus 4. Okay, now let's graph a bigger one. And then after that, I will graph the strange one. Something big in the sense that the base is not 2, like number, let's say number 20. Number 20. Let fx be negative 3 to the negative x plus 9. Now, I say this is big because we need a bigger graphing paper. I'm sorry. Because instead of attacking this graph directly, I'm sorry, my screen seems to be, yeah, this is a better view. Okay, instead of attacking the graph directly, let's answer those questions of, let's say, what's the domain? Well, that's an exponential function. So the domain is all real numbers. How about the range? Then let's take a look on how the graph actually moves. Okay, originally it's 3 to the x. So it is an increasing function with 3 dots here, right? And then replacing x by negative x, you basically reflect with respect to the y-axis, right? So now the 3 dots becomes like this, right? And then negative 3 to the negative x, which means we reflect that upside down, right, with respect to the x-axis. And then we add 9. And then we add 9 means the horizontal asymptote, originally y equals to 0. Now horizontal asymptotes y equals to 9. Okay, but those 3 coordinates are now here. Okay, now from the graph, you see that the range is from negative infinity up to positive 9. So you will see that if you have exponential function, right? Okay, that gives us horizontal asymptote y equals to 0. Now, this guy, the constant, will give us the horizontal asymptote 9 because you move it up, or if the constant is negative, you move it down. Okay, so it has something to do with this. Now, how about part C? How about the y-intercept? Y-intercept, f0 equals to negative 3 to the power of 0 plus 9. That's negative 1 plus 9, that's 8. So the y-intercept is 0, 8. How about the x-intercept? You set the y equals to 0. Okay, let me move the negative 3 to the negative x, becomes 3 to the negative x equals to 9. And then this is 3 to the negative x equals to 3 squared. So negative x equals to 2 or x equals to negative 2. So the x-intercept is negative 2, 0. Okay, now then the horizontal asymptote. As we have said in the sketch earlier, y equals to 9. Now, my graphing paper is not as big. I don't have y equals to 9, so I will use my nodes graphing paper. So I will use this. Let me start. So I start from here. Oops, it's way too high actually. Hold on. Okay, now then the y-intercept 0, 8. So 1, 2, 3, 4, 5, 6, 7, 8. X-intercept negative 2, 0. Horizontal asymptote y equals to 9. Okay, and then how about those three important coordinates? Again, originally is 3 to the x, right? So 3 to the x is the y-intercept is 0, 1, 1, 3, negative 1, 1/3. When we reflect with respect to y-axis, those three coordinates becomes negative 1, 3, 0, 1, 1, 1/3. Now then, when we reflect with respect to y-axis, those three coordinates becomes negative 1, negative 3, 0, negative 1, 1, negative 1/3. So approximately this is the graph look like before you move it up 9 units. When you move it up 9 units, then you will get these three coordinates. Let me enlarge this so that we have better view. So this will be here and here. Now, like we have said before, if the base is big, then the graph turns a lot sharper. The graph turns a lot sharper. Like it gets flat out really early, really fast, but then it shoot to infinity a lot faster too. Okay, that's what the graph look like. Now, the thing is because we anticipate in case later on you don't print your tests, you use blank paper, so you need to graph your coordinate system, right? Then make sure you label the, for example, the horizontal asymptote y equals to 9, and these important coordinates here. Okay, this is 1 comma negative 1/3 at 9 will be 8 2/3. This is 0, 8. This is negative 1, 6, and this is 2, 0, negative 2, 0. Okay, so if you don't use graphing paper, if you don't use graphing paper, then make sure you label them. Now, let me show you what happened, what it's supposed to look like if you don't use graphing paper. Then it will look like this. Do you see that? Okay. In other words, without the grids, if you don't have grids, right, and you label them, this is what it looks like. Without the labeling, if you don't label it, then I will not know what are the coordinates, right? If you don't label it, then you cannot really tell what is your graph. Okay, you need to label it. Okay, you need to label it if you don't use graphing paper. Does it make sense? Okay. Now let's go back to normal view. Now, my intention in your test, I usually use base 2 or base 1/2. Okay, base 2 or base 1/2. Sometimes I use some a little bit stranger base, but let's do one. Let's do one. The base that's kind of a bit strange but still doable using our technique. Now, my technique is always usable. The thing is, because the base may be strange, then my graphing paper may not be big enough, okay? Or my graphing paper may be too big that the details not visible. Now, let's say, for example, we do this one. Let fx equals to 0.4 to the x minus 2 and then minus 1. So first, what is the domain? Then what's the range? What's the y-intercept? The x-intercept. How about the asymptote? And after that, we graph. Okay, as usual, the domain is all real numbers. The range, the function is decreasing down to 0 for this, right? That's decreasing down to 0. Okay, and -1 here, move it down 1 unit, right? Okay, so the horizontal asymptote now, y equals to 0. Okay. Now then, the range will be from -1 to infinity. The asymptote is y equals to -1. Now, how about the y-intercept? So f0 equals to 0.4 to the -2 minus 1. Ooh, that one is hard to compute. I don't recommend you to use calculator right away though. No, I don't recommend you to do so. How do we compute 0.4 to the -2 without calculator and to keep the accuracy? 0.4 is 4/10, right? Okay, which we can reduce by 2/5. Now, to the power of -2 means you flip that to make it positive exponent. Okay, and then this is 25/4 minus 1. That's 21/4. Now, then the y-intercept will be 0.5 and 1/4. Is it okay? What I'm afraid is this. What if I use 0.3 instead of 0.4 and you just rush to calculator, right? And you will not get correct, or you will not get a precise y-intercept. You will get a decimal with a long decimal. Okay, that's for the y-intercept. How about x-intercept? Let me do it. Let me do it here. Part D. The x-intercept. We set the y to be 0. So move the 1, but 1 is 0.4 to the 0. So 0 equals to x minus 2, x is equal to 2. So the x-intercept is 2, 0. Okay, now let's get to the graph. Give me a second. The y-intercept is 0.5 and 1/4. 1, 2, 3, 4. A little bit more than 5. The x-intercept is 2, 0. The y-intercept is y equals to -1. Now the thing is, what happened to what happened to the 3 important coordinates we supposed to have, So originally the 3 important coordinates are 0, 1, 1, 0.4, -1, 2.5. How do you get that, Thomas? 0.4 to the power of -1 is 4 over 10 to the power of -1. That's 2/5 to the power of -1, which is 5 over 2, which is 2.5, right? So when x equals to -1, when x equals to -1 in the basic function 0.4 to the x, the graph will look like this. Okay, now then imagine those 3 important coordinates. You move 2 units to the right. 2 units to the right becomes here. 2 units to the right becomes here. 2 units to the right becomes here. And then from there, you move 1 unit down. 1 unit down becomes here. 1 unit down. Oh, that's the x-intercept. That's right. Okay, and then this 1 more unit down becomes here. So those 3 important coordinates now rest at these 3 places. I now connect the coordinates, connect the points. Okay, this is our y equals to 0.4 to the x minus 2 minus 1. Okay. Now, I will spend a little bit more time in graphing question number 23. I think I did number 24 in my lecture, so let me do number 23. how do we handle the situation when we have number 23, fx equals to 2 to the absolute x. Now, this goes back to the very basic about absolute value. We know that absolute of x is equal to x when x is at least 0, equals to negative x for x less than 0. So you can say that, Thomas, I know the graph of absolute x, it looks like a V. Now, the thing is that doesn't really help. That way of visualizing absolute x does not really help once you put this absolute x as the exponent. Okay, now it's better for us to see, oh, absolute x is equals to x when x is positive. Therefore, for 2 to the absolute x, it will be 2 to the x for x is positive, and it will be 2 to the negative x for x is negative. So we are creating a piecewise defined function. Okay, we are creating a piecewise defined function. So basically on the positive side, we will graph 2 to the x. For the negative side, we will graph 2 to the negative x. Okay, so 2 to the x on the positive side will be like this, 2 to the x. That's the graph of 2 to the x on the positive side. Okay, it's supposed to look like this. This is 2 to the x, right? That's what 2 to the x look like. Now I only graph the positive branch. Okay, so I only graph the positive branch. I get it from here. Now then, how about 2 to the negative x? Then I graph the negative branch of 2 to the negative x. It's supposed to look like this, 2 to the negative x, right? Okay, but I only take the negative branch. Okay, so let me use this guy. So this guy here give us this. Okay, now actually we can also see it another way. We can also see it another way. We can see it this way. Oh, you know what? This function is an even function. Why? When you use f negative x, that's 2 to the absolute negative x, which is 2 to the absolute x anyway, right? In other words, f negative x is equals to fx, right? Which implies, for this function, which implies this function is even function. Therefore, it has y-axis symmetry. Is that right? Now, if it has y-axis symmetry, what we can do, we graph the positive branch first, and then reflect that with respect to the y-axis, while keeping the original copy. So you will see that it's actually sharp here, by the way. It's not rounded. It's not rounded. It's not rounded like x squared, you know, it's not rounded. It's actually sharp. It's actually sharp. Okay, to be more precise, it's a corner instead of just round. It's actually a corner, like that. Okay, at the vertex. Now, this is how you graph the ones with absolute value. So basically, you go back to this basic definition of absolute of x, okay? And then you put it back there, give you this. Okay? Now, next, oops. What if they give us the graph? What if they give us the graph and we need to find the equation? What if they give us the graph, but we need to find the equation? Let's say, for example, we look at number 32, which I think I already did in my lecture. So let me do number 31 instead. Number 31. The sketch of the graph looks like this. The graph looks like this. We have coordinates 0, -1. And we have -1, 0. And we have horizontal asymptote y equals to -3. So the graph approximately looks like this. Okay, that's all we know. That's all we know. That's y equals to -3. And they also tell us that this is the graph if the graph has the form fx equals to b times a to the x plus c. Find that function. Find that function. Now we will start with the horizontal asymptote. Horizontal asymptote, y equals to -3. That will be our c. Okay, so fx is b times a to the x minus 3. Well, because horizontal asymptote for any exponential function is y equals to 0, right? It becomes -3 here because of the constant. Okay, now then next we will use the y-intercept. The y-intercept is 0, -1, which means when I plug in x equals to 0, that is equal to -1. Now, but a to the 0 is just 1, right? So b minus 3 equals to -1. B is 2. That's the coefficient. Okay, let's update our function now. So the function is fx equals to 2 times a to the x minus 3. Now then here comes the x-intercept, -1, 0, which means when x is -1, the y is 0. So a to the -1 is 3/2. So a is 2/3. Therefore, our function must be fx equals to 2 times 2/3 to the x minus 3. Okay, that's for number 31. Okay, No, I think that's where I will stop for this 4.2. Let me go on to 4.3. 4.3 is the natural exponential function, which I believe I already mentioned last time. Did I? I somehow think so. Give me a second. Give me a second. Now, 4.3 is a special case of exponential function. So 4.3 is natural exponential function e to the x. Now, there are many definitions of e, but let's just use approximation. E is approximately 2.71. I think I should say 2.72. Okay, now our textbook define E as this. Our textbook definition from our textbook says that E is actually coming from 1 plus 1 over n to the n when n goes to infinity. Okay, in calculus 2, we actually need to prove that. Okay, we actually need to prove that. In calculus 2, the way it is being defined is then when x goes to infinity, 1 plus 1 over x to the x. That's equals to E. Okay, our calculus 2 textbook by Stewart defines E differently. You need to look at the textbook and learn the derivative to understand how Mr. Stewart actually defined it though. But Mr. Sokowski in this textbook defined it as this. So Thomas, which definition you use and do you even care? Well, I don't care. But the one I prefer as my definition is the one our textbook's using. Okay, or when our text. You can try using Excel to approximate this E. You know what? Let me try to do that. Let me try to do that. I wonder if I can do that here. Give me a second. Give me a second. Wait. Give me a second, okay? I need to look for that because I delete Excel from my I delete Excel from this computer. Remember last time they messed up? Okay, let's use Excel. So I will do the following. Let me enlarge this so that you can see better. Okay. Let's say this is my n, and this is my 1 plus 1 over n to the n. Okay. So when n equals to 1, what will that be? That's equals to parentheses 1 plus 1 over whatever number we have there to the power of whatever number we have there. Supposed to be 2. Okay, now then let's make it when n equals to 2, what is that? What happened when n equals to 3? And so on and so forth. Do you start seeing that? When n equals to 4, that's 2 to the 2.4444414, right? Okay. And again, I will just make it bigger here. That's when n equals to 7, the last one. Let's do more. That's up to 10. When n equals to 10, then that expression 1 plus 1 over n to the n is 2.59. Now, what happened if I make it 100? What happened if I make it 1,000? What happened if I make it 10,000? Now, you see that from 1 to 2, from 2 to 3, it increased actually quite fast. But when n becomes very, very big, it increased just a very little bit. Okay. Now, if I make this instead to be 1 million, 1 with 6 zeros, it doesn't change that much anymore. You see that? Okay. Let's make it 1 billion. Let's make it 1 billion. So enlarge this. 1 with 9 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. See, it doesn't change even to 5 decimal places. Okay. Now, then from there you see, oh, you know what? Then that's what our, let me screenshot this and then put that on our node. Okay, that's our definition. Now, how do we use this? I will not really do much here. I let it go to your calculus class to talk about this exponential function. For us, I would just say that this e is just a constant, approximately 2.72, such that when we have e to the x, when we have y equals to e to the x, then the function will still be an increasing function. Okay, the function is still an increasing function. Oh, I'm sorry. Oops, I'm sorry. I already changed to here. Okay, yeah, I changed this. Now, if I have y equals to e to the x, then the graph is the y-intercept is 0, 1, 1, 2.7 something, and negative 1, 1 over 2.7 something. So that's what the graph looks like. It is still increasing. It is still increasing from left to right. The coordinate 0, 1. This is 1, e, and this guy here will be negative 1, 1 over e, like that. Okay, now this section is more about how to use and apply this into our application in daily life. The one I'm interested to explain, to use with you is, for me, I like this very much, is how we use this for compound interest. How we use this for compound interest. Now, original formula is the following. Okay, if principal P is invested invested into an account that pays interest R annual interest R compounded n times in a year for T years, then the amount in the investment after T years is given by amount after T years is equals to P times 1 plus R over N to the power of NT. Okay, let's say for example, as I remember, I never really asked this kind of question in my test. I may want to ask this in your quiz, but this is more into how you use your money, okay? For example, suppose you have the principal of $10,000 and you deposit that into account that pays for 3% annually. And that account gives you interest every month, which means it is compounded 12 times a year. And let's say you deposit that for 10 years. Then the question is, how much money do you have at the end of that 10 years? Solution. The amount of money you have after 10 years is the principal $10,000 multiplied by 1 plus 3% in decimal divided by 12 times to the power of 12 times 10 years. Now, from there, you just use your calculator to compute. Okay, so that's 10,000 times 1.0025 to the power of 120. That's how much money you will have at the end of 10 years. Now, some logic, why? Why does it look like that? Here's the idea. Let me use this example. Okay, we start with $10,000, right? Okay. Now, the annual interest rate is 3%, but you do it 12 times a year. So the monthly interest is 3% divided by 12. So if you deposit $10,000 right now, then next month your money will be $10,000 plus the interest of that $10,000. Is that right? which I can write as 10,000 times 1 plus 0.0025. Is it right? Now, then what happened the next month after that? Then you will have interest from your principal. You will also have interest from that interest. So the interest you get in the first month will receive further interest from that interest. So the interest get interested too. That's what we mean by compound interest. Okay, but you see that every time we jump 1 month, you basically multiply by 1.0025, right? So the second month, how much money you will have? The second month you will have 10,000 times 1.0025 times another 1.0025. So this is the amount of money after 2 months. The amount of money after 3 months will be to the power of 3. Now, then you deduct further and further, then how much money you have after 120 months, which is 10 years. Okay, that will give you this amount of money. This is how you compute how much money you have after you deposit certain money in a bank. And this is exactly the formula they use in the bank right now, because in the bank, they do compound interest monthly. Okay. When they do compound interest monthly, then the end is 12. Now, but there are cases where the interest is being done continuously. Continuous compound interest formula. That is when n goes to infinity. What happened to that formula? Let's say you compound it every seconds for 10 years. Okay, P times 1 plus R over n to the power of nt. What will happen if the n goes to infinity? When n goes to infinity, then the formula becomes P times e to the rt. Okay, so using the example we have earlier, suppose you deposit $10,000 at the interest of 3% annually, compounded continuously. and you deposit it for 10 years. Then how much money you have at the end? And there will be the amount of money after 10 years is 10,000 times e to the power of 0.03 times 10. That's how much you will get at the end of that 10 years. Okay, now how do we use our calculator to compute this? Now, I only have TI-84 on my computer. And that's what I will use to show you. Give me a second. It's still calling the function. Okay, then how do we compute the one up there? The one up here. 10,000 times 1.0025 to the power of 120. So 10,000 times 1.0025 to the power of 120. That's $13,000, 493.54. So that's, what is that again? 13,493. So $13,493.54. That's how much money you will have at the end of 10 years. If you deposit $10,000 right now in an account that pays for 3% interest annually, compounded 12 times a year, basically monthly, for 10 years. Now, if the compounding is done continuously, basically they do the compounding, they do the interest every seconds, right? Every half seconds, every split of seconds, then the amount you have at the end of 10 years will be given by this expression here. And to compute that, that's 10,000 times e to the x. It's here. For my calculator, it's e to the x here. So second e to the x, okay, 0.03 times 10. That's 13,498.59. 13,498.59. Okay, so some people may ask, oh, Thomas, don't you think that if we compound it more often, then the money we have at the end of 10 years will be more? It is true. But the thing is, however often you compound the money, there's a limitation how fast your money can grow. Okay, once the interest rate is 3%, okay, even if you compound it continuously, like every seconds, every 1/10 of a second you take the interest, at the end of that 10 years, the money you have is only, compared to compounded monthly, is only $5 more. Okay, it's only $5 more. Oh, by the way, American interest right now is actually very small. It's like around 1% only. So if you deposit your money in American saving account or maybe deposit, the interest you get will be around only 1% per month, per year. Indonesia has 6% per year. Now, if you are going to a business, if you take pre-calculus and end up going to do business, take a look on the interest rate in other countries. Okay, try to find out. Like for me, for example, if I have extra money and I see that the situation in Indonesia is quite stable, right? Then I will actually deposit my money in Indonesia instead. Why? Because the interest rate is better there. Okay, and I was told that I think is it in Peru? The interest rate is like 20-something%, even 60%. The higher the interest rate of a country reflects the more unstable the economy. Like the higher the interest rate means the government needs more money. Okay, now that usually implies the inflation is to be very high also. Okay, now of course there are other things that we can do using this E. Beside you using this for money, we also use this for radioactive decay or population growth, right? But not only those though, we use E in a lot of things. And one of the use of E, another use of E is in predicting our pandemic. So this E is very, very far-reaching numbers. This E, as I remember, comes from the name Euler. Let me confirm that. Our textbook usually, yeah. I think this E comes from the person who coined this term first, and his name is Euler. That's how they use E here. This E is not for exponent, no, it's for this guy named Euler. Okay, now what do you need to really remember from this class, from this 4.3? The only thing you need to remember is what this E stands for, approximately 2.72. That's all you need to remember. Okay, that's all you need to remember. And everything else, you basically just use calculator. Okay, will I ever ask you the compound interest questions? No, maybe in your quiz, but your quiz, you have time to look at the book, look at the notes, right? I don't think I will ask you that in your test. Even if I do, I will give you the formula. Okay, even if I do, I will give you the formula. Okay, but nothing much to say here. And every time we work with problems in this section, they will give us the formula. Okay, let me give myself a little break. And then after that, we go to 4.4. We come back at 4, I'm sorry, at 4, at 9. Right now it's 9:20. We come back at 9:30. Okay, see you later. Okay, we will do 4.4 now. Again, the assumption is, I assume that you already watched the lesson from my announcement 5 up to lesson 13 for today. Okay, you should have watched up to lesson 13. But I think the beginning of this 4.4 actually in lesson 12. We are slightly 1 day behind schedule. We are 1 day behind schedule. So make sure you already watch up to lesson 12. But very likely it's in lesson 12, but maybe it's also in lesson 13 as well. Now, 4.4 is on logarithmic function. Now, the theoretical part that I need to emphasize from our lecture, first one is definition. Oh, yes, you're right. This 4.4 is not in test 1. I'm sorry, not in test 2, but is in test 3. Thank you. Oh, the one I need to emphasize is the definition that if we have 4a positive and not equals to 1, a to the x equals to y is the same to say is equivalent to log base a of y equals to x. Okay, keep this in mind. We call this the exponential form. We call this logarithmic form. Okay. Now, things that we will learn from this section. First one, we will practice on converting exponential form to logarithmic form to exponential form. We'll spend like around 10 minutes in working on that. And then after that, we will learn to sketch the graph. Actually, no, solving equation first. Solving simple log equation. Yeah, in there we will also see some basic properties of log. And then we will learn to sketch the graph. Okay, now let's take a look on a problem from our textbook. This is a good view already. Okay. So for example, let's take a look, for example, number one. Nothing really hard from exponential form to logarithmic form, from logarithmic form to exponential form. Trust me, it's very easy. If you find it to be hard, then you must be thinking way too hard. Okay, please think simple. Okay, I'm not saying that, oh, you need to be smart. No, it's learning pattern. Okay, it's learning pattern. Let's play this way. Suppose I have, for example, pound to star equals to triangle. That's exponential form. Then what will the logarithmic form be? That will be log base pound of triangle equals exponent. Okay, we call this the base. The exponent becomes the answer. And this is the argument. Okay, memorize that pattern. So, for example, number 1a, we are given 4 to the power of 3 equals to 64. That's exponential form. Then what is the logarithmic form? Log base 4. Now the base is a subscript, smaller and lower. Log base 4 of 64. This 64 is written regular way, equals to 3. Okay, the 4 is a subscript. The 64 is regular. Now, I saw some people, they write it this way. Log, the 4 is regular size and the 63 is very like up there. That's not the right way to write it. No, that's wrong. That's wrong. The 4 is supposed to be smaller and lower. The 63 is supposed to be the same size, the same line, the same level with log. Okay, so it's supposed to be log, the 4 is small and lower, the 63 at the same level, at the same size with that log. That's the correct way of writing it. Okay. Now part B. Still we are given exponential form. 4 to the power of -3 is 1/64. Then what is the log form? That's log base 4 of argument 1/64. And I usually use parentheses for the argument if it is a fraction. Okay, equals to the exponent -3. Part C. I hope you follow me in writing. Okay. T to the R equals S. That's the exponential form. Then the log form will be log base T of argument S equals to R. Okay, the better you are in doing this, the better you will be later on to solve equation. This is so basic. When I say so basic, not in the sense that it is so easy. No, it is so basic that in the sense that it is so important. If you want to be successful in this section, in log and the rest of this chapter, you need to be really good with this kind of conversion. Okay, now 3 to the x equals to blah. What will that be in log form? That's log base 3 of blah equals to the exponent. And we need to use parentheses there because if I don't use parentheses here, it means the log only applies to 4 instead of 4 minus t. Okay, so I need to use the parentheses there as the grouping of 4 minus t. Part E. We have 5 to the 7t equals to a plus b over a. Now, what will that be in log form? The base is 5 log base 5 of parentheses a plus b over a, right? That's the argument, equals to 7t. Okay, and then part F, 0.7 to the t equals to 5.3. Now, what will that be in log form? That's log base 0.7 of the argument 5.3 equals to exponent t. Now, that's for number 1, in which we convert from exponential form to logarithmic form. Now, let's see the other way around. Number 3, where we are given log form, and we need to rewrite it in exponential form. Log, part A, log base 2 of 32 equals to 5. What is the exponential form? The base is 2, the exponent is 5, the argument is 32. That's it. Am I too fast? I hope not. Part B. Okay, let me slow down. Yeah, part B. Log base 3. Log base 3 of 1 over 243 equals to -5. Now the base is 3, right? This is the base. To the exponent -5 equals the argument. Okay, so from log form to exponential form to from exponential form to log form is something they expect you to be able to do swiftly, fast, and nearly without thinking. Okay. How can you not thinking when you do math, Thomas? You can if you get used to it. So my point here is not about that. It's not about computing here. No, this is not computing yet. We don't compute anything yet. We just change the pattern. We just change the form, in this case from log form to exponential form. Log base t of r equals to p means the base is t, the exponent is p, the argument is r. That's it. That's all they want. Okay, now part D. Log base 3 of x plus 2 equals to 5. Now, what will that be in exponential form? Let me ask you to do that. These three questions here. Part E, log base 2 of m is equal to 3x plus 4. What will that be in exponential form? And part F, log base b of 512 equals to 3 over 2. What will that be in exponential form? Okay, let me give you maybe 1 minute for this. So this will be base 3, the exponent is 5, the argument is x plus 2. Now, they don't tell us to solve it though, even though we can, but no, they just want us to rewrite it. How about number part E? The base is 2, exponent is 3x plus 4, the argument is m. Part F, the base is b, the exponent is 3/2, the argument is 512. Okay, now we will leave the solving later on. They have on the next page of our textbook, you will see we will do solving log equations, but let's do that later. Number 5. The question is solve for t, number 5, 7, and 9. Solve for t using log base a. Number 5. We have 2a to the t over 3 equals to 5. We need to solve for t. So what we will do first, we will isolate the exponent part That's 5 over 2, which is 2.5, right? Which is 2.5. Now then rewrite this, that's exponential form. Now rewrite this in logarithmic form. That's log base a of the argument 2.5 equals to t over 3. Now think about this first. A to the t over 3 equals to the argument. So what will t be? Well, multiply by 3, both sides, right? 3 log base a of 2.5 equals to t. Okay, you will see to solve for the exponent, you need to first rewrite it as a base to some power. Isolate a to some power. Number 7. K equals to h minus c a to the t. So I will subtract by k. I will add by c a to the t. And then divide by c. Now notice that the reason I divide by c so that I isolate the exponent one side. No more coefficients, no more constant, just something to some power. Now then from there, I rewrite that into logarithmic form. Log base a of the argument h minus k over c equals to that t. Okay, now let me give you 1 minute to do number 9. A equals to b times a base a to the ct plus d. Let me give you 1 minute to solve for t. So first I will subtract by d divided by b and then change it into log form, log base a of a minus d over b, that is equals to ct. Then divided by c. Okay, that's when we try to solve an equation, but this is basically without numbers, right, or parameters. Now, furthermore, some special cases. To be more precise, special basis. Log base 10 of x is also written as log x, where the base is not written. If you don't write down the base, it means it is base 10. Okay, by the way, this is a convention. Thomas does not invent this. This is not from our textbook. That's a convention. If you don't write the base, it is base 10. Just like square root of x. If you don't write the index 2, we understand that as square root. Okay, if it is cube root, you have to write the 3, right? But if you don't write the 3, that means square root. Now, that kind of convention, okay, that kind of convention. So going back to the log, if you don't write the base, then it is base 10. Okay, now, if you see log base, if the base is e, then it is usually written as natural log. Okay, in other words, natural log is a log with base e. That's what it means. Okay, special base, special notation. Okay, let's say, for example, number 11. Number 11a, we have 10 to the 5th equals to 100,000. Now that's exponential form. What will that be in logarithmic form? Log base 10, which we don't write the base anymore because it's base 10 of 100,000 equals to 5. We don't write the base because it's already base 10. Part B, 10 to the negative 3 equals to 0.001. And in log form, we don't write the base 10. We just write log 0.001 equals to negative 3, and that's it. Okay, part C, 10 to the x equals to y minus 3. Then the log form will be log base 10, which we don't write the base, y minus 3 in groups equals to 3x. Part D, how about e to the 7 equals to p? What is the log form? Now, because the base is e, we use natural log. Natural log means log base e of the argument p equals to 7. Now, part E for that number 11, e to the 2t equals to 3 minus x. Then the log form will be natural log of argument 3 minus x equals 2t. Just like that. I hope you find it to be that simple. Okay, how about number 13? Number 13, we go backward. We start from exponential form, going to start from logarithmic form to exponential form. Part A, log x equals to 50. Now the base is invisible 10, right? Okay, so when we write that into exponential form, that 10 then appears 10 to the 50 equals to x. Part B, log x equals to 20t. What will that be in exponential form? As the base is 10, the exponent is 20t, the argument is x. And that's it. Part C, I mean. Natural log of x equals 0.1. The base is, that's natural log, so the base is e, the exponent is 0.1 equals to x. Now part D, natural log of w equals to 4 plus 3x. So the base is e, the exponent is 4 plus 3x equals w. And finally, part E, natural log of argument z minus 2 equals to 1/6. What will the exponential form look like? That's e to the 1/6 equals to z minus 2. Okay, now notice that I spent quite some time just for this conversion from exponential form to logarithmic form to exponential form. That's how basic and important it is. When I say basic, it is not in the sense that it is easy. No, you will see it is actually easy, but it should come from you getting used to it. Okay, yes, it starts from memorizing. Okay, and once you apply that, not only memorizing, simply because you know it now doesn't mean you will remember that tomorrow. You need to get used to it. Okay, you need to get used to it. And you need to get used to it such that you remember this for the rest of your life. Not only for this course, but once you are in calculus, especially calculus 2, where we deal with derivative and integral of log function, exponential functions. You will see that more. Okay, but Thomas, I don't need calculus 2. I just need calculus 1. And that's fine. And good luck. Okay, but I don't think that you will not see log anymore for the rest of your life. You will. Okay, now with those said, let's go on to computing some basic properties of log. Number 15. Part A. Compute log base 5 of 1. Log base 5 of 1. What is that equals to? If you happen to memorize the basic properties, then you can just answer this directly. Now, what I will do right now is to develop those basic properties. Okay, so after this number 15, we will have basic properties for you to memorize. And the work is basically done in this number 15. How do I compute log base 5 of 1? If I don't memorize that, then the first thing you do is you make it equal to x. And we will compute that x. Okay, I'll call that x for now, and then make it into exponential form. In exponential form, this is 5 to the x equals to 1. Oh, but 1 is 5 to the 0, right? From there, we see that by 1 to 1ness, x equals to 0. Therefore, log base 5 of 1 is equals to 0. Okay, that gives us basic property number 1. Basic property number 1. log base A of 1 is equal to 0. Okay, for A positive and not 1. For the base positive, not 1, log base A of 1 is 0. Part B. Log base 3 of 3 equals what? Again, if you don't know, you write it as an x. Call that x. And then change it to exponential form. But 3 is basically 3 to the 1. Therefore, x equals to 1. In other words, log base 3 of 3 is equal to 1. Now, that gives us the second property, the second basic property. Log base A of A is equal to 1. That's for part B. Let me move this down. Oops. Move it to the right-hand side here. Okay. Part C. How about log base 4 of negative 2? Again, if you don't know, if you don't memorize that, call that x first, but then attack that from exponential form. 4 to the x is negative 2. But then you realize, oh, there's no such thing. Note that from 4.2, we know that the range of 4 to the x is positive number. Right? So there is no x such that 4 to the x give you negative 2. This is no solution. Okay, which if you see that that's because the argument is negative such that it has no solution. Okay, the argument is negative such that it has no solution. Now that brings us to point number 3. Domain of y equals to log base A of x is x has to be strictly positive. Okay, so the argument of log has to be positive. The argument of log has to be positive. Part D. Log base 7 of 7 squared equals to what? Again, if you don't know, call that x. Then convert that to exponential form. Oh, they have the same base, right? Base 7. Okay, then by 1-to-1ness, x equals to 2. Therefore, log base 7 of 7 squared is equal to 2. Now, in other words, log base A of A to the n is equals to n. For any positive base not 1, log base a of a to the n is equal to n. Part E. Then how do you compute 3 to the log base 3 of 8? What is that equal to? I don't know. Call that x for now. Call that x for now. But you see this is actually exponential form. The base is 3. The exponent is log base 3 of 8. The answer is x, which is the argument. Now then, because it is exponential form, I will rewrite that into log form. Log base 3 of x is equal to log base 3 of 8. Now, since exponential function is 1-to-1, then you will see log function is also 1-to-1. Therefore, log blah equals log bleh means blah equals to bleh. In other words, 3 to the log base 3 of 8 is equals to 8. That leads us to basic property number 5. A to the power of log base a of x is equals to x. Okay, now those are 5 basic properties. Those are 5 basic properties of log. I need you to memorize this. Okay, the next section, which we will do on Thursday, is on on properties of log. But this is the basic property. Like something you need to know even before we talk about other properties. Okay, now once you know this, we can do part F and G supposed to be easily. Part F, let's say, what is log base 5 of 125? Log base 5 of 125. Now, if you don't know, call that x. Okay, and then you rewrite that as 5 to the x equals to 125. But 125 is 5 cubed. So from there we see, oh, x equals to 3. Right? And so log base 5 of 125 is equals to 3. How about part G? Log base 4 of 1/16. I don't know what's that, call that x. Okay, Thomas, what if I know that? Then you still need to show your work, right? So that's 4 to the x equals to 1/16. We can write 1/16 as 1/4 squared, which is 4 to the -2. So x equals to -2, which implies log base 4 of 1/16 is -2. Okay, that's for number 15. Now, one of the key components of this section is, and I want even to call this a theorem, that log functions log function is the inverse function of exponential function. Emphasize this. Okay, emphasize this. In other words, if fx equals to a to the x, then the inverse function is log base a of x. Okay, I believe you have seen that proof, but let's do it anyway. Okay. Now, of course, the condition a to be positive and not 1 should be satisfied. Proof. I do it again because this is how important it is. Okay, let fx equals to a to the x. So step 1, to find the inverse, replace fx by y. Step 2, you swap x and y. Step 3, you change into log form, log base a of x equals to y. And step 4, inverse function of x is log base a of x. Okay, so I have proven that log function is the inverse function of exponential function. Now, consequently, as you have seen from 4.1, consequently, one of the very big consequence is that log function is 1-to-1. Remember that exponential function is 1-to-1, right? Exponential function is 1-to-1. And because it is 1-to-1, we can find the inverse function, right? Right? Because the function is 1-to-1, then the inverse is also a function. Inverse is also a function. So the inverse exists and it is a function. Once I give you a function, the inverse always there. But how to make the inverse also a function? Then the original function has to be 1-to-1, such that the inverse is also a function. But the free stuff after that is that the inverse is also 1-to-1. Now, that's what we use here. Okay, in other words, that brings us the following. Log base a of blah equals to log base a of blah implies blah equals to blah. Okay, that is a very important conclusion. There are other consequences besides that log function is 1-to-1. For example, the domain becomes range becomes domain, x-intercept becomes y-intercept, y-intercept becomes x-intercept. Horizontal asymptote becomes vertical asymptote, but we will talk about that on Thursday. Okay, let's just use this consequence first, that log function is 1-to-1, to solve log equation number 21. Solve log base 4 of x plus 10 equals to log base 4 of 8 minus x. Okay, log equals log. Then solution. If log equals log means the argument has to be the same. Okay, log of the same base means the argument has to be the same. So 2x equals to -2, x equals to -1. But before we are done with this, you need to do some visual check. Okay, you need to check, at least visually, that when you plug that into each argument, the result is still positive. Okay, so make sure this x always give positive argument. In other words, when you plug that x equals to -1 here, you get positive. In this case, positive 9, right? When you plug that here, it's also positive. Okay, so in this case, i.e. in this case, -1 plus 10 is positive. 8 minus -1 is also positive. Now, what happens if you get negative? Then you cross it out. It's not even in the domain of the log. Remember, that's basic property number 3. Okay, the domain of a log function, the argument of a log has to be positive. It cannot even be 0. No, even 0 is not okay. It has to be strictly positive. Okay, number 23. We solve log base 2. I'm sorry, it's log base 3. Log, oh, no. I look at the wrong question. Log base 5, not base 2. Log base 5 of x minus 2 equals to log base 5 of 3x plus 7. Because they already have the same base of logs, then the argument must be the same. Right? So -9 equals to 2x, right? Okay, divided by 2, then -4.5 equals to x. But the thing is, I have to cross this out. Let me use red color so that you see that. Cross this out. Okay. Because -4.5 minus 2 is negative. Okay. Once it doesn't satisfy the log, the argument of the log to be positive on any one of them. So you can check this one here, or you can also check this one here. Okay. Once any of them becomes negative, then you have to cancel that solution. Okay. So in this case, you will say no solution. Okay. Now for the rest of this section, for the rest of this solving part, it's basically the same. Okay, number 25, for example, let's solve log x squared equals to log of -3x minus 2. Log blah equals log bleh implies blah equals bleh. And then you solve it. Set one side equals to 0. So we get x plus 2, x plus 1 equals to 0. So x equals to -2, x equals to -1. Now, then you plug that -2 here. -2 squared is +4. That's okay, right? -2, plug that in here. Let's see. -3 times -2 minus 2. That's 6 minus 2. That's positive. So -2 is okay. How about -1? -1 squared is -1 squared is 1. That's positive. -3 times -1 minus 2. That's 3 minus 2. That's still positive. So both x equals to -1 and x equals to -2 are okay. You don't even need to check if they are equal. You just need to check if it satisfies the argument has to be positive. Okay. Now the rest of this part, number 27, 29, 31, 33, 35 are doable. And on Thursday, when we come back, we will continue with this 4.4 on the graphing part. On Thursday, we will continue with this 4.4 on the graphing part. Now, I would like you to make sure you watch lesson 13 and lesson 14, such that on Thursday, when we come back, we can finish the graphing part and do the properties fast. Now, property of logarithms is something you have seen in math, in intermediate algebra. Okay. So once we are done with this property of logs, which is short, we will go on with solving exponential and logarithmic equation. And see you then on Thursday.